We're starting activity 17 about dilations, which are size changes, and similarity transformations. This video is for lesson 17-1. We're going to discuss dilations. This video is going to have a lot more pauses in it for you to take notes on your packet, and this is a little bit different than what the other lessons have been earlier this year. Learning goals are to perform dilations on a coordinate grid and perform dilations on plain paper, and also to use symbols to describe dilations. The application referred to in this activity is the size change done by graphic artists. Here we have the layout for two pieces of artwork. Layout A is this larger image, layout B is the smaller image. The first thing we're asked is, what are the coordinates of the vertices of the pre-image shown in layout A? This vertex at point A is 0, 8, so I'm going to write that down. Now I'm going to pause the video for you to figure out the coordinates of the other vertices in layout A. In question 2, we're asked for the coordinates of the vertices of the image shown in layout B. So in the second drawing, point A is located at 0, 4. Let's write that down. And then I'll pause the video for you to write down the coordinates of the other three corners. Question 3 asks, what relationship do you notice between the coordinates for layout A and the coordinates for layout B? Take a look at layout A. We have 0, 8, and then look at its corresponding vertex in layout B, 0, 4. What relationship do you see? Looking at point B, this is 6, 8, and in the other one, 3, 4. What's the relationship between the 6 and the 3 and the 8 and the 4? Can you put that into words? The coordinates in layout B are half those of layout A. Now, how can we express that transformation as an algebra function? We've written algebra functions for other transformations earlier this year, such as translations, reflections, and rotations. And the way that that was done is to write down the ordered pair symbol, x, y, to draw an arrow, which meant goes to, or changes to, or is transformed to, and to write down an algebra expression that explains the mathematical relationship between the original number and the new number. In this case, it's 1/2 of that original number. And that was the same for the y coordinates as well. The y coordinate in the new drawing is half the y coordinate from the original drawing. So here is our algebra function. So layout B was a reduction of layout A. Now let's consider the situation where layout A was enlarged. So here we have a picture of layout C, and we can look at the vertices to see how they compare to that original layout A. What relationship do we notice? So let's scroll back to layout A and take a quick look at the vertices, and then we can compare the y value 16 to the y value of the original point A, or we could compare the x coordinate 12 to the original x coordinate of point C to see what happened. I'll pause the video for you to write down that relationship that you notice. So the coordinates of layout C are twice those of layout A. Now write an algebra expression that shows that idea of being twice as much. And it would look like this. The ordered pair x, y transforms to 2 times x, 2 times y. This idea of changing size by reducing or enlarging an original figure to create an image is called a dilation. So here's the definition of dilation. It's a transformation that changes the size of a figure, but not its shape. It changes the size by a scale factor, k. So we're using the letter k to be some number that tells us how the size is changing. The scale factor determines whether the transformation is a reduction or an enlargement. Now question 8a, what is the scale factor for the transformation of layout A to layout B? Remember that we had expressed in words what happens when it changes from layout A to layout B, and we had even written an equation for that. Layout B was half of layout A. So our scale factor is a half. So when we're asked what is the scale factor, we can write down k equals a half. K is the number that you multiply by to change the size of a figure. Now I'll pause the video for you to answer question B. Question C asks, what is the scale factor for the transformation of layout A to layout C? So look back just a little bit, find the work that we had done on changing from layout A to layout C, and figure out the value of K. Once you do that, then answer question D. So speaking in general, for what kind of numbers for K do you think we have reductions? Dilations are reductions when the value of K is a fraction. So when K is between 0 and 1, a figure will reduce in size. This can be rewritten with algebra symbols as 0 is less than K is less than 1. This is saying the same thing as this phrase that I wrote on the screen. Now number 10, in general, for what values of scale factor K is a dilation and enlargement? Enlargements occur when the scale factor is greater than 1. That can be written in algebra symbols as K is greater than 1. Now number 11, a pre-image point, let's say it's capital P, has coordinates A, comma B. So we're using the variables A and B to represent whatever the numbers are for that point. How can you find the coordinates of the image of P after a dilation with scale factor K? So we're taking our example with actual numbers and we want to generalize that into a theorem that explains how to use scale factor to figure out the coordinates of the image. What we have figured out is that we can multiply the scale factor to each coordinate. So we can multiply K to A and to B. Multiplying the original x and y values by the scale factor K will get us the x and y values of the image. We can show this sentence using function notation. If we have an original ordered pair, x comma y, and we multiply it by the scale factor K, that will create the image under a dilation. So x comma y transforms to k times x comma k times y. This is the general theorem that we follow in order to figure out the coordinates of an image. Let's apply that theorem with an actual problem to make sure that you can use it correctly. There's a rectangle that has coordinates A, B, C, and D with these ordered pairs. Let's say that it's mapped onto rectangle A prime, B prime, C prime, D prime by a composition of transformations. That is more than one transformation. The first thing that's going to occur is that the x values are subtracted by 4 and the y values are subtracted by 6. Do that first. Then apply a dilation with a scale factor of 1/2. So take whatever coordinates you get when you do those subtractions and multiply them by 1/2. So I'll pause the video for you to figure out where A prime and B prime, C prime and D prime are located. Here are the answers. And here's how I got those answers. Let's just consider point A prime. Point A is located at 0, 6. I first subtracted 4 from the 0, getting -4. Then I multiplied by the scale factor of 1/2. 1/2 times -4 is the -2. Now for the y coordinate. I subtracted 6 from the 6, getting 0, and then I multiplied by the scale factor of 1/2. 1/2 times 0 is 0. So that is why A prime is located at -2, 0. The next page of the book discusses dilations where the center of the dilation is not the origin. In our geometry class, we're only going to work with dilations where the origin is the center. So we're going to skip this next page. In earlier activities this year, we did transformations called translations, reflections, and rotations. When we first learned how to do these, we did use a coordinate grid. But later, we did these transformations on plain white paper. Sometimes we used a ruler to help us make the picture accurate. Dilations can also be performed without a coordinate grid. A dilation centered at point O with scale factor k can be written in function notation as, and then here you see the symbols used. So the capital D tells us that we're performing a dilation. As a subscript, we have the letter O. That's going to refer to the center of the dilation. Then there will be a comma and then whatever the scale factor is. If it's a number that's a fraction, then we can assume we have a reduction. If it's a number greater than 1, assume we have an enlargement. In parentheses, this will be our original figure that we're going to dilate. And then over here, this will be the symbols that we use to label our new figure. This is telling us to use the prime in the corner. Now right below, we have a sample of this situation. So let's say point O is a center, and here's point P. The distance from O to P could be measured on a ruler. Let's just make believe that it is 1 inch. To perform a dilation with scale factor 3, we want to move in the exact same direction, but we want to multiply that distance by 3. So we would put a ruler starting at point O, stretch the ruler in the same direction, and go 3 inches, and that would locate us P prime. So we'd put the ruler right there at O and stretch it across 3 inches because 3 is 3 times the 1 inch. And that's how you locate the new position of a point. If this was a figure instead of a single dot, the process would be the same. Let's say that there was a triangle located here. Maybe the triangle has letters in the corner, A, B, C. Let's say that the center of our dilation is right there. There's our origin where we want to dilate from. Let's say that we want to make this larger by multiplying by scale factor of 2. So you would lay a ruler from that dot right to that corner, measure that distance, and then double that distance, which would locate you about right here. If that dot was capital A, then we just found A prime. And you could do that same technique for the other corners of the triangle as well. You would stretch the ruler from there to there, and then go in the exact same direction twice as far. If that original point happened to be point B, then we just found B prime. Do the same thing for the third corner of the triangle. When you get all done, you will have made the triangle twice as big. Here would be that new triangle. Let me shade that in just so it shows up better to you. So here is how you perform an enlargement or a reduction on plain paper. You would need to have a ruler so that you can measure distances and double them or triple them or times them by 4 or whatever the scale factor is telling you to do. So in this video we discussed dilations, which are size changes. We did a couple examples using a coordinate grid and also without a coordinate grid where you would use a ruler and use plain paper. We were able to describe our dilations in words using words such as the new image is half as big as the original. We can also describe dilations using algebra functions.